Hi all, nice meeting you. Today, I'm going to talk about how you can use Braket for your hackathon. I'll start with running through the console. I don't have any slides to share. I'm just going to run through the console, and I have a couple of our colleagues, Peter and Sebastian, who are doing support on the chat as well on Twitch. So please ask any questions on chat as well. For the hackathon, you would have received credits for using Braket service. If you don't have an AWS account already, you need to get one created. If you have, I'm going to show through how you can redeem your credits, how you can enable and set up Braket. You can follow along while I'm doing it, but this session is recorded as well, so you can do the similar setup after as well. So the first step is to redeem the credits once you have created your AWS account. So for that, so once you log in, for those who are new to AWS, I'm just going to run through the console itself. So it's fairly straightforward. If you go to the home page of the console, you get some recently visited tab, some of the applications if you have configured, and general dashboard. One key thing to notice is the regions. So AWS services are distributed across different regions, and you get to select which region you're going to work on. A Braket service is only available on few regions, so it's important to pay attention to that. So first, for redeeming credits, you click on your username after you've logged in, and go to billing and cost management, or directly from the console, you can start in the services part. You can start typing billing here, and you can get to billing cost management directly as well. Once you are here, you click on credits, and click on redeem credit. So you type in the credit you have received, the promotion code, and the CAPTCHA security part, and then click on redeem credit. So as soon as that's done, you should have credits added to your score. So when mine is currently empty, so you'll see the credit here and the total amount. And as you keep using, you will have the total amount left visible here in the billing console. So the next step is to enable billing alerts, because especially if you're using credits, it's important to make sure you're not keeping an eye on it and you're not accidentally using up too much of it. So for that, you go into preferences and enable alerts. For receiving billing alerts, you edit, and then you enable billing alerts. So if you're a new account, you have free tier as well. So if you can also select to receive alerts when you exceed any free tier limits. And for this is email address. You type in your email address and click on update. So that enables alerting for you. Next is to enable access to third-party QPUs that are available on Braket. So once your account is set up and you have enabled billing alerts, you go into services and look for Braket. And go into permissions and settings as a first step, and enable third-party devices. So this is an one-time activity on an account. So once it's done, it is enabled. So this basically allows access to third-party devices. So this is mainly to read through the terms here on how the third-party devices are used from Braket, and then you click enable. And if you're planning to run some of the hybrid jobs, there are two steps to do here. One is service-linked role. Click on that create service-linked role button to click that. So this service-linked role is allowing Braket to access your AWS resources on your behalf. So basically storing your results, running programs in other services of AWS for running your quantum circuits. And there is a feature called hybrid jobs. We'll look at that in a bit. Here, there is another requirement to enable, create a default role for running this hybrid jobs. So click on verify exit roles. Mine is already here, so it's showing which role is existing. If it doesn't exist, this button will be enabled. So click on the create default role button here. So basically, as soon as you log in, go into Braket, click on permissions and settings, enable third-party devices, and create service link role and the default role. So these are the two initial steps to get you started on Braket. Right, so let me walk through the Braket console itself and what is available here, how you can navigate and use the Braket service. So in dashboard, you have access to resources. There is a Braket digital badge for certification, so you can go through the learning path and achieve that Braket badge as well. Access to documentation and the algorithm libraries are here, and announcements and the devices and simulators. So we'll look at each of these separately. So let's start with devices. Braket has multiple simulators and QPU hardware from different vendors available. So this is giving you a full list of all the devices and simulators you can use using Braket service. The first three are simulators: state vector simulator, a tensor network simulator, and a density matrix simulator. And then different hardware providers. From IonQ, we have 4 different devices available. From Oxford Quantum Circuits, we have Lucy, and QEra have provided Aquila device, and Rigetti's Aspen device. So OQC and Rigetti are superconducting devices. IonQ is a trapped ion device, and QEra is a neutral atom-based QPU, which is using Rydberg atoms. For all of these devices within Amazon, when you want to use, it's not just for these devices, across all of AWS resources, we have a unique identifier for a resource. It's called an ARN, Amazon resource name. If you click on any of the device ARN is available here for simulator. So this is the ARN you will specify when you're building a circuit or you want to submit a job to a simulator or to a QPU. For any of these devices, you can click a device and then look at different details. One is the details of the device itself, the availability window, which region it is. So that's the important part. Where it is located, and pricing details. And also, you can also get the topology and the calibration details for each of the devices. So these are the device details. Next, Braket provides a managed notebook service. So go into the notebook. So when you create a managed notebook here, Braket creates a Jupyter notebook using one of the other services called SageMaker, but that's all hidden away from you. You can just click this create notebook instance, select a name, and then there are many types of instances that support this Jupyter notebook. So here for now, we'll go with standard, but if you have any specific requirements for running local algorithms, the classical part, you can go for GPU accelerated or high performance CPU ones as well, or you can custom, there are many types of instances available. You can choose the right one that is needed for your use case. So we'll go with standard here, and you can select the volume size. If you're doing it for the first time, I would recommend click on a create new role. What this does is it creates a role and then attaches that role to the notebook you're creating with all the permissions needed for running the Braket jobs. And if you already have a role created, you can select from the list. So all these are different roles we have used in the past. So I'm going to go with create new role, and then the rest you can leave default. So this is just a summary, and then click launch. So this takes about 6 to 8 minutes, roughly, just over 5 minutes-ish. Once this is created, it will automatically open, but you can always go back to notebooks. And one I created earlier today. Once it's created, it'll become in service, and you'll have a URL to access the notebook instance. I have it here. So if you click on the link, it opens the notebook Jupyter Lab environment in a new window. Right. So this notebook instance has got all the Braket SDK and the dependent libraries all pre-installed. And also it has a copy of 2 repositories from GitHub. One is Braket examples, another is Braket algorithms. Within Braket, I'll just quickly show algorithms, and then I'll come back to Braket examples, which will go a bit more deeper. So within the algorithms, there are a few textbooks for common algorithms, where you can, there are libraries that make, instead of starting from scratch, you can use these higher level libraries in your applications and directly from. There are examples of how you can use all these different algorithms, and you can use these in your applications directly. Okay, let's go into examples. So here we have many categories within the examples folder. Getting started is a good place to get started. So I'll go through how the Braket algorithm is used. I think this is the QPU one. Yep. So if we look at the native Braket SDK and how to use that here. For the Braket SDK, we have a cost tracking as an enabler, which you can start the tracker when you start when you are starting the execution of a notebook. I'll also, after showing this part, I'll also show how you can set up billing alarms in a repository. Or one of my colleagues, Nihir, has shared a CloudFormation template, which you can run to set up billing alarms. I'll cover that in a bit, and I'll share the link for this repository as well. So you enable the cost tracking as you start the executions. And within Braket SDK, you have local simulators and also simulators that are managed in AWS Cloud, and also QP devices. So here we're just doing some standard imports and then importing circuits and devices from the Braket SDK. So this example notebook walks through what devices are supported and what gate sets are supported in each of those devices. So this is just picked 3 different devices from 3 different providers for the gate-based programming. QEra is not gate-based, so it is a special different paradigm of programming, and there are examples separately for that folder. So these 3 devices, you can get all the gates that are supported directly from the SDK, and this is for everything that's supported in the SDK itself, and then the different gates that are supported by different devices. So we'll look at a simple build state circuit. So here we're adding a Hadamard and a CNOT. So the way you construct the circuit here is you instantiate the circuit instance and then start adding gates. So this is done in one line, but once you have a circuit, you can, so we'll run this part and show you the circuit. But then you can also, once you've added, you can append more, like for example, X. If I say 1, so that adds X gate to qubit number 1. So just run this and print and show you the difference. So now it has added an X gate to qubit 1. And you don't have to predefine the qubits. You can always add like, so hold on, sorry, I didn't run this. Sorry, excuse me. There you go. So that is run now, and you should see additional qubit added to the circuit. So you can build these circuits dynamically, and you can also define these subroutines and programmatically build your circuits as well. So the SDK is very flexible on how you build and parameterize your circuits. There are many examples which go into very much details. Go back to the standard build circuit, and then first run it on the local simulator. So for local simulator, you don't even need an AWS account. So you can download this from GitHub and run it locally on your, once you have an SDK installed, you can run it locally on your laptop as well. So here, once you define a device, the way to run the circuit is a device.run, and then within the brackets, you give which circuit to run. So the circuit name you defined earlier, and the number of shots. So that's the way to execute a circuit. And this triggers a task. Because it's a local simulator, you'll not see that in our console directly. So it just runs here locally. And then to get the results back from the run, you can from the task that creates a task. From the task, you create use the results subroutine to get the results. And from the results, you can get the measurement counts, and then as you can see, it's roughly 526 and 474, and you can plot these. To switch to QPU or a managed simulator, for example, the only way is straightforward. You specify the ARN we talked about from the console. You can also get that from the SDK. We'll look at that in a bit. So we are setting up a device. So currently, we'll just pick OQC as an example. OQC has got longer availability during this the QHack. So we suggest you can use OQC for gate-based and IonQ as well. So IonQ, there are multiple devices. And also QEra for cold atom-based problems. So when you define, instead of local simulator to run on a device or a simulator, you define a variable and specify the ARN of the device itself. And after that, it's the same method. The only thing is, if you're running it on a QPU, the results, I would recommend keep them separate, because otherwise the task will kind of wait until the circuit is run and you get the results back. and that can vary depending on how busy the devices are and when they're available. So I'm going to submit this job here in OQC, and so that task has been submitted. Same build circuit, and it has been submitted on OQC. It's currently offline, so it's not going to run now, but it'll be queued. So this is what I was talking about. So if you go into quantum tasks, you will see some tasks here when you submit the task, but it's not visible here because we are in the North Virginia region. So wherever you run the job from, even though the notebook is in North Virginia region, the task itself will only run on the region where the devices are. So OQC is in London, so you have to switch to London region to look at those tasks. So this is the task we just created, UTC 2021. So that's the task we have created. So if you go into the task, it will have the details of number of shots, which device it's going to be run on. And once it is actually completed, you'll also get the results linked directly here. So let's switch back to North Virginia. Right. So that's very high level of how you can create and run on a device. Let's maybe run the same circuit on a simulator. That's SV1, the state vector simulator on Braket service. So here we are defining a GHC circuit. It's a parameterized circuit where you can pass in the number of qubits you want to build in a circuit to the function. I'm going to jump into the simulator directly. Hold on, sorry about the scrolling. Okay, SV1. So you are going to use SV1 to submit the task. So SV1 is a state vector simulator. It's a managed simulator running on infrastructure within AWS. So you're defining the device as SV1, and here we are specifying the number of qubits and 15. So it's a GHC circuit which maximally entangles 15 qubits. And then it's the same thing. You run it on the device. So the device is SV1, and you run GHC and then 1,000 shots. And you get the results back, and the measurement counts from the results object, and then we can plot it and see the difference between all ones and zeros. Right, we have run now, so we have seen the results all zeros and ones. It is a state vector simulator, so there is no noise, so you get these perfect results. Obviously, you're not going to get this on QPUs. So now we have run this in the region, which is North Virginia. So now if you go and refresh this, you should see a task here. So this is the task we just ran, and you see the task details here. So and the results I was talking about. So you can click on this. It'll take you to the S3 bucket where all Braket results are stored, and you can analyze those results there as well. The next thing I want to talk about is hybrid jobs. So hybrid jobs is a fully managed orchestration of hybrid quantum classical algorithms, where it's combining classical cloud resources like EC2 compute, say the containers or other instance types, along with QPUs. So the tasks that are created using hybrid job, they have higher priority queuing over individual tasks. So this is mainly because if you are running an iterative process, you want to make sure you run it on the device when it is in the similar config. So when you submit a job, the device is kind of reserved for that duration until your tasks finish. So you get higher priority access to the device you're running. So mainly to avoid any fluctuations within the device. So for each QPU, there is a separate queue for hybrid jobs. And at a time, only one hybrid job can run on a particular device. So if you look at the device, if you pick any device, there was the number of tasks is really high, actually, over 4,000. There's another two queues here. One is priority tasks, that's different, and then hybrid jobs queue depth. So this is currently, so this is what I was talking about. So when you run it using the same task using hybrid jobs, mainly for the iterative, you get better access to the QPU. So let's, so what we are going to now look at an example is using PennyLane. So PennyLane and Braket SDKs are like they work together very well. So here we are going to use hybrid jobs and PennyLane to run a hybrid job. And there are, we have recently announced a hybrid job decorator, which is used to make running your hybrid jobs much efficient, the PennyLane jobs directly. So all you do here is, we'll come to the decorator in a bit. So let's start how you can run PennyLane jobs in Braket. So it's, you import your standard libraries. And currently we're going to initially start with the local qubit, which is the local simulator from Braket. In PennyLane, you can define as braket.local.qubit, and the number of qubits here, that's the number of wires. So you import it and you define the circuit using these decorator, qml.qnode, and the device, so which is your defined here. So this is a standard rotation, 2 gates, Rx rotation and RY rotation in with different parameters. And then we are measuring expectation value on the Z basis. So that's the circuit. And then, so this is a routine where we are defining a qubit rotation with number of steps and different step sizes. And this is standard PennyLane way of doing. There's a lot of documentation on how you can use PennyLane and how you can use with Braket. Quickly, I'm not going to go into all the details of how you configure this. I want to show how you can use hybrid jobs with PennyLane in a bit. So this, so if you define the qubit rotation, we are running this using the local simulator. So it's now running quickly and showing you the number of iterations and different values. Now, if you want to run this as a hybrid job, all you do is you define your circuit and your program, and then you instantiate using this a decorator, a hybrid job. And so here you pass in the device name, and you can refer to the documentation on what syntax is supported for different devices. So here we're going to use local, the same device, and define that. Oops. Did it run? No, didn't. Sorry. Yeah, that has run now. So now, when I run this, so when you add a decorator, so when you call this program, instead of returning these parameters, what the program returns is actually the job ARN. So what happens is this creates a hybrid job, and the job details are returned as output of this particular function. So I'll run this, and then we'll go into the job and look at the details. Right, it has run and it has created a new job. So now you can look at the state directly from the SDK here itself. It's currently in queued state. Now let's go into the console and look at hybrid jobs. So that's the job we just submitted. It's on local Braket default. That's what we did earlier. So if you click on the job, so every Braket job takes some time to instantiate because it has to spin up a classical resource, basically a container. Braket comes with 3 default container images, one for a base image with standard Braket SDK, one for PennyLane with PyTorch, and one for PennyLane with TensorFlow. But you can also bring your own container image. So you can, there are example notebooks to help you build your own image as well. And you can bring that along here. So there's also another advantage of using hybrid jobs is you can use embedded simulators as well. So there are easy to instances types which have GPU. So if you want to run a simulation, quantum circuit simulation that can use GPU, you can use these hybrid jobs as well. So you can run these in like multiple, if you want multiple GPUs in the same instance or run parallel across multiple GPUs, you can use hybrid jobs. There are some examples, again, using PennyLane and multiple GPUs on how you can use these within the examples repository. Right now it's running. So once it's running, you can look at the events here. So how long? So it starts up an instance, downloads the standard image, and then when it says downloading the data, this is the circuit you are submitting and the instructions where it has to run. That is getting downloaded as well, and then the execution starts. Once the execution starts, you can look at the logs in CloudWatch. CloudWatch is our monitoring service, which supports logging from multiple AWS services, but you can also write your own mechanism to write log data into CloudWatch. And one other feature of hybrid jobs is, it's already run and completed. So you can look at the logs in CloudWatch. So you click on that link, it opens CloudWatch. For each job you're running, it creates a log group, and there are direct links to go directly into the one that's specifically for the job we created. And so here you can, so these are the initial setup for the hybrid job itself, and you can look at different parameters, and you can use hyperparameters to pass on different variables and control your iteration. So here this is just a simple rotation we saw in different expectation values, and it's the 10 different iterations. So this is just a simple example, but you can have a long running job with like hundreds of iterations to go through. So as part of the submission, I kind of skipped this. There is a facility to do log metric. So what this does is it starts logging after every iteration. It's updating a CloudWatch metrics, which you can monitor directly from the console, this monitor tab. So it starts logging the metrics, so you can actually see how your function is converging or not directly in the console. And if you see it's already converged, or if you achieve the results you're looking for, you can terminate the job early to save costs. Or if you see that even after like 300 iterations it's not converging, you may have to tweak, you can cancel it as well. So another advantage of the hybrid jobs is you can look at the quantum tasks here if they are running on like managed simulators here. We are running on the local qubit, so it's basically running on the container locally, so it's not submitting a quantum task per se, so that's why you don't see this. Right, so that's hybrid jobs at a high level. And it's the same thing, the example goes through and uses the same library to change to a different queue, so you can specify a QPU as a device ARN, and then pass the same thing to hybrid job. The rest of the program is pretty much the same. All you need to specify here the device ARN and the decorator. Those are the only two places you have to change, and then the rest will run as you have here. So that's all the demo I wanted to do. Any questions so far?
We did have quite a few questions, but
sorry.
No worries. We did have quite a few questions, but Peter and Sebastian pretty much answered all of them.
Okay.
So yeah. Sorry, keep going.
So there's one more thing I wanted to say. There is so we talked about billing, and we enable billing alerts, but if you want to configure when do you want alert, there is a URL here. Which I can share. So you can implement this particular, you can clone this repo, and there are this enable billing alert CloudFormation template. You can use that to enable billing alarm. Maybe I will quickly show that if there are no other questions. So you go into CloudFormation. I will share the link of the repo in the chat. And so if you go into CloudFormation, make sure you download this file here. Enable billing alert. So you go into CloudFormation. The repository itself has the instruction on how you do it. So I'm just wanted to make sure you're following it through here. So this is the part which talks through how you enable it. So you create stack with new resource, upload the file itself. Sorry, no underscores allowed. So here we are saying after $50, send an alert to the email. So you can adjust this on when you want your alert to be sent, and then click next a couple of times. There are no other. So this creates a billing alert, and it will alert you whenever when you are reaching that threshold you have set. And once you have set the billing alert, so you need to log the billing. So we talked about the cost tracker when you are running on the notebooks. So we saw here at the beginning in the previous notebook when we looked at, and you need to use that and use this function in your notebook as part of your executions. That way you are tracking the Braket cost directly, and when you add this, then you will see alerts within your email when you reach a particular threshold. That's all I had from a demo perspective. I'm happy to take any other questions or anything else you want me to cover based on the chat.
Sure. I think, correct me if I'm wrong, moderators and Peter and Sebastian in the chat, but I feel like everything got answered. Oh, here we have a question from Panos Const, actually. What's the advantage of using cloud-based simulators instead of doing things locally?
It all depends on how powerful local machine you have.
Exactly.
So my standard Mac, I can simulate up to maybe 24 qubits on a state vector simulator. Mm-hmm. After that, you run out of memory and all the power you need. In the cloud, the state vector simulator we have supports up to 34 qubits, and Tensor Network Simulator, which supports up to 50 qubits. So you can simulate up to 50 qubits in a Tensor Network Simulator. So that's, and you don't need to pay for a very heavy machine. So you're only paying for the amount of time the simulator is used. And that's the advantage of using simulators in the cloud.
Yeah, Panos Const, every high performance computing thing will pretty much be accessed through like a server or something like that. Yeah, so pretty much everything high performance HPC is cloud based to some degree. Another question from Iverlin. Sorry, I don't know how to pronounce your username. Is there? Sorry, I got to scroll up here. Is there a way to automatically stop all processes when you're out of credits? When you're out of credits?
There isn't an automated way.
Okay.
So that's why we are recommending use billing, because you
Right.
specify a credit card when you create an account, and that you have to keep an eye on it. So that's why you create an alarm. There's also budgets you can set in the billing, which is additional way. So overall, so here the billing alert we talked about is specifically to Braket. But if you go into the billing console, there's also something called budgets. You can set that as well. So if you go into budget and you can set a particular amount, again, you'll get an email only. So there isn't an automatic way of stopping you from not running it or stopping your resources when you reach a particular thing.
Right. Had a question from Andres Ulid. Sometimes doing calculations on a GPU can be expensive on the cloud. Yeah, there is actually a free tier for Braket that includes an hour a month for free. So thank you, Sebastian, for putting that in the chat. Yeah, GPUs are in high demand, and still I think the supply chain and stuff makes them scarce to some degree. So such as economics, I guess. But Braket has 1 hour a month for free. So there's that at least. No problem. Okay, so if we don't have any more questions, actually, Jagadeesh, I kind of wanted to ask you some questions personally. So we were chatting before this. You said that you'd been with AWS or Amazon for 6 years. What did you do before this role that you're in right now, or were you always in this role to some varying degree?
I have been a solution architect in AWS for the last 6 years. I've been supporting different customers. I'm based in the UK. Mm-hmm. I've been supporting different customers, and quantum computing is my hobby and passion. So that's why I'm doing this almost as a side job. My day job is supporting life sciences customers in UK.
Oh, nice. Okay.
And I'm part of the quantum team and helping customers in EMEA as well.
Right, cool. What's your background in? Is it physics or something adjacent?
I did I'm not a PhD holder. I did a physics degree, and I have interest in this quantum area. But my job-wise, my background has been infrastructure, both servers, networking, and storage. That was
interesting. Okay,
background.
Cool. I'm not a PhD holder either. I just have a master's. I say just have a master's. I'm very proud of it. But anyway, no, I'm not a PhD holder either. I just couldn't do it. I think that's becoming less and less of a thing, honestly. Like, it used to be like PhD and that's it. PhD or bust. Now it's not quite that. So thank goodness for that.
I work with lots of PhD holders within the quantum team. So it's
Oh yeah. Same with me. Actually, Guillermo in the chat here. Guillermo, I think you're starting a PhD, I think, but Guillermo works with me at Xanadu. He just has a bachelor's currently. I say just as well, like as if it's like something that it's like not as good or whatever, but totally is like very respectable, obviously, right? Cool. How did you get started in quantum computing? Like, what was your first foray into this field? Was it quantum computing specifically, probably just based on your background, or was it physics? What was it?
It was my interest started when I started learning about the quantum physics, but then I almost didn't do anything until I got into AWS, and when I learned that's when Qiskit was getting popular as well and more mainstream. So I started in Qiskit learning before Braket was a thing. I was playing around with quantum in Qiskit and attended the summer schools, and that's about time when Braket was getting started as well.
Right.
And I've been working with the Braket team almost from the beginning on the sides and trying to contribute whatever I can, mainly on the testing side, and getting to know the Braket SDK, running it, experimenting, and also running workshops for customers, and just playing around and learning in the process.
Do you remember what your first contribution to Braket was?
I wrote contributed to some of the example notebooks.
Okay.
in the repository and also to the algorithms library.
Okay.
So I wrote the Shorts part as part of the book. So my contribution was to the Shorts algorithm notebook.
Cool. Right on. All right. Well, I think we'll wrap it here. Again, thank you to Sebastian and to Peter for being in the chat, answering all the questions. And to Yudo says, thanks, Jagadeesh. Yeah, thank you, Jagadeesh, for joining us today. We do have another talk from AWS. I think it's Zaya that's going to join us this afternoon for half an hour. Yeah, another great comment here. Great orientation to Amazon Braket. Yeah, definitely. We do have a video as well on Amazon Braket, specifically the hybrid jobs feature. I think Alvaro put that in the chat. Yeah, just scroll up a little bit, and you can click on that. We did a demo on like how to use hybrid jobs and stuff like that with PennyLane. So definitely go and check that out. Jagadeesh, it was a pleasure to have you on here. Thank you for spending your evening with us here. Hopefully you enjoy the rest of your Friday night. Have a great weekend. Thanks for participating in QHack, and yeah, have a great night.
Thank you, Isaac. Thank you for having me.
Cheers.
Cheers.